It is a real pleasure to have Sanja Fidler here today. Sanja is well known in the computer vision community. She probably is one of the people who doesn't really need an introduction. She has recently been awarded her tenure at the University of Toronto. She's also director of AI at Nvidia, and she has published so many papers, and they're all so good papers. It's really hard for me to pick a few out. I was a big fan of the Pac-Man GANs, but of course she has been doing a lot of other work. And I'm also super happy that she's been recently going into more in the 3D direction. And so we're really happy to have you here. I'm really curious what you're going to talk about.
Yeah, thank you, Matthias, for inviting me. It's really exciting to be virtually in your lab. Yeah, so today I'm going to mainly talk about our work that we've been doing at NVIDIA. And so as you guys know, I hold this dual position. So I'm a faculty at U of T, but I'm also I hold this industry position. I lead a research lab of NVIDIA in Toronto. And this lab basically started 2 years ago, maybe a little bit more than 2 years ago. So what you're seeing here is kind of like a first launch. It was CVPR 18. And yeah, so since then, the lab has grown. So right now we have 13 full-time employees, 14 starting next week, and a full bunch of interns. And what you're going to see is basically hard work of these amazing people. All right, so when I joined NVIDIA, I didn't really, I kind of wanted to find my space where I could contribute. And you see pinging, right, in the back? I'm really sorry about that. I think Slack is making some noise.
It's all right, don't worry, it's all good.
Yeah, and I figured that NVIDIA was at heart a computer graphics company, and they were doing so much AI, and computer graphics and AI has really been going, have become more and more powerful over the recent years. And I don't know whether you guys have seen the recent Ampere launch by Jensen out of his kitchen. It's basically this new compute architecture, and along with it was like the first GPU in this series. And this is making, AI and computer graphics and all these different areas of compute like significantly faster. I think the speed ups you can get is about 20x. And I just wanted to share a video that I just kind of really love watching. This is too loud. But basically what you're seeing is being rendered in front of your eyes. So it's real-time photorealistic rendering with dynamic lighting, physics, everything computed real time. And it's basically graphics and AI working together. So AI is helping with graphics to be rendering this. And all this is being rendered in this new platform called Omniverse that is going to be released in the coming months. It's a platform for 3D rendering, visualization, and collaboration. And you can see that this has millions of faces, these polygon scenes, and all the lighting and everything is completed. All right, cool. Yeah, so graphics and synthetic content plays a role in a lot of different domains, right? So in architecture, you have architects design interior or office spaces. It's all about designing these CAD models in virtual reality and rendering before you actually go and build it. Gaming, all these new games are have this really intense 3D content. Everything is in 3D. Even in movies, a lot of the movies are actually exploiting graphics just because directors want too much from animals and even people. And of course, these days VR plays an important role, right? You might want to see a tiger in your room or maybe virtually drink a beer with your friends. And then there's also simulation, which is something that I'm particularly excited about. So in healthcare, so robotics for operation, something like operations, and then autonomous driving, and warehouse robots. All those fields actually need simulation as like playground before you can actually deploy those robots in the real world. You want to test them against all sorts of different challenging scenarios, right? And for that, you need really good 3D content that is realistic. It looks like your target real world, as well as really challenging scenarios that are gonna produce some some measurable performance that's going to translate into real world performance. And this is really kind of like my main motivation, right? So if you want to build something like a simulator for self-driving, right now what you're seeing here is hundreds of artists and engineers designing this. But in the end, you get something really good, right? So you get basically this Ego cars practicing here, but the cool part is that not only you can vary the environments, you can have different weather conditions, different sign, different number of cars and so on. You can also render grunge fruits for free. You don't need any labeling because everything is done in 3D, right? You have those labels already in 3D. So you can just render them in separate channels, right? Semantic segmentation, normals, materials, all that comes out for free. So you can actually help train better AI algorithms as well. All right, great. So, how can we as AI help here, right? So imagine that, I just want to take some 3D model of a city or different cities or different worlds from, an online warehouse or something like a marketplace like TurboSquid. Right? You get something like this, like geometry that you see in front of you. And how can we make this city be alive? Right? How can we now turn this into a simulator or even into a game? How can we actually help this artist to make this geometry kind of become alive? I think that's one of like dreams basically for me. Right? And I put this to test. So we had an artist in the Nvidia office, and we asked him to replicate the scene that you've seen above. So this is a scene from Kitty, and below is an artist that already has all the assets that kind of look similar. So the only task was basically to arrange them properly, to figure out the good
Manual
layout.
content creation pipelines require significant human effort. Here, we see a person creating a scene aligned with a given real-world image. The artist places scene elements, edits their poses, textures, as well as scene or global properties, such as weather, lighting, camera position. This process ended up taking 4 hours for this particular scene.
Yes, this was 4 hours, and it's not even like a perfect match, right? So imagine how much time this takes. And I'm sure, many of you have played with a GTA game, Grand Theft Auto. And if you look at on Wikipedia, this game takes such an enormous time to create. So it was about 3 years with 1,000 people working on this. And if you read into the details, basically what they've done is, go around the city of LA and took 250,000 of photographs. I don't know how many hours of footage. And then they have artists kind of look at that and try to replicate this 3D world and behaviors in this game engine, right? And I feel like this is really kind of where we as the AI or 3D vision community can come in and make this process a lot faster, right? All right, so what kind of tools I think would be really cool here to build? And what I'm going to talk about today is really just scratching the surface. And I think you guys also have done a lot of really good work in this domain. And I'm really hoping the community continues to work on this. Right, so one thing is we want to synthesize worlds. So basically placing objects in the right way. With, for simulation, we want to be as realistic as possible, but maybe for gaming, we want to have some artistic control over how these layers are going to look like, right? Maybe cars can fly in a game engine, whereas they cannot do for a real world simulator. Then we want to create assets, or at least maybe tools for assets or objects. It's going to help artists create this content much faster. And then there's a dynamic aspect of scenes, right? You want to have a way to maybe learn or model these behaviors much faster, so avoid kind of writing these behavior trees or whatever they're doing in gaming, and have maybe more realistic animations that requires maybe less human effort to create. All right, so I'm going to present, what we have been working on this particular domain, and it's really, I think, just the beginning. I'm going to talk about first how we can use AI to learn how to synthesize worlds. And when we started this, we kind of turned to game engines and how they are doing this in a scalable way. And we noticed that many times they use so-called probabilistic grammars or procedural models to create scenes basically in a valid way by imposing some sort of rules. So for example, to synthesize a traffic scene, you would have obviously a road, and then you would sample some number of lanes, but maybe you have some constraint need to be parallel or whatever. On each lane, you would sample some number of cars, and next to a lane is always a sidewalk or sometimes a sidewalk, right? And then you have a sample some number of persons on the sidewalk. All right, so basically this whole generation is driven by this probabilistic grammar, where you have basically some nodes that represent the class of the object we're placing in the scene and attributes. And these attributes basically instantiate this object in the scene. So you would have like a location, a height, a pose, color, and so on, which potentially you can randomize. So here is just an example of how a scene is being sampled, where these attributes just have like uniform distribution. So, the scene doesn't look so good. And basically the artist needs to define this distribution such that the scenes that are being sampled actually look good. So in this particular case, they need to create or design good distribution for the structure, how many lanes, how many cars typically appear, as well as the distribution for the attributes. Typically cars need to be aligned with roads and things like that, right? So in the first part of this talk, we're just going to talk about how can we learn these distributions? How can we learn these distributions from data, right? So we want to be maybe taking some footage from a car driving around, and we want to be able to automatically learn how to synthesize these scenes. And the advantage of learning this from some target footage means that I have a scalable way of going to model LA to Tokyo, potentially. Okay. So this is what we call Metasim. Essentially, we have a simulator model that the artist writes, and then we're going to learn some parameters of that simulator such that the resulting images are going to look like target data. And we're basically training this in kind of 2 or maybe 3 carefully designed stages. And in the first step, we're just gonna take this, let's call it like an initial probabilistic grammar, like a prior, where the artist has designed some reasonable distribution for the attributes. And we're gonna take that as kind of face value. We're gonna sample a lot of the scenes from these probabilistic grammars. And basically the goal is going to be, we're going to keep the structure of those sample scenes. We're going to freeze the structure across the training, but we're going to try to learn to modify those attributes to match the target data better. So the first step in this training is just going to be autoencoding. So essentially we have like a graph neural net to represent each scene. And that takes into the initial attributes in this case, and then it's going to try to produce, modified attributes. And in the first step, we're going to just try to reconstruct back the input. So, kind of like an auto-encoding objective. And in the next step, we're bringing real data into the loop. So essentially, we're going to further train this graph neural net to repredict these attributes such that when you render that data, it looks similar to the target real scenes. And really how we're implementing this is a distribution matching measure, which is in this case a maximum mean discrepancy, MMD, which basically takes a batch of real scenes, in this case, a batch of rendered synthetic scenes, and compute some sort of a distribution metric on this. And we propagate that back to the graph neural net. And obviously here, the renderer is not differentiable, at least we haven't used a differentiable renderer. So this is all done with numerical gradients by perturbing each of the parameters. Notice that in this case, no labels are required. Everything is done by just comparing images. And in practice, we encode each image into some feature space and do the comparison in the feature space. And this turns out to work really well already. But we have an additional, let's say, optimization on top that one could potentially employ if you have a little bit of label target data for the task that you care about. Right? So ultimately, we want to learn the scene generator such that it produces good-looking images on which we can use some AI that potentially can be deployed in the real world, right? So if the user defines, okay, I want to train a basically a synthetic data set with really good objects for detection, then maybe we can actually optimize our scene generator for that particular task, and maybe even for that particular neural architecture. So essentially what we're gonna do here is, through apex of training, we're gonna synthesize some small data set. We're going to train this black box neural network on top for the task at hand. We're going to compute the score on this like small label testing set, and then we're going to just propagate back that score back. And of course, this is non-differentiable, so here we're just using RL. And this is also a very expensive step, so we do this only a few times during training. Okay, so for results on the right side, you have a couple of examples from the Kitty data set, just random selection. On the left is the samples from this initial probabilistic grammar, so where these attribute distributions are kind of set by hand, not too carefully. And then in the middle are these scenes optimized with this Metasim approach. So to me, this was quite interesting because we're not using any labels, yet the method kind of learned how to align cars with lanes and bring pedestrians closer to the camera, because this seems to be what is happening in Kitty, and so on. So this is going to show what's actually happening during training. So the first frame is just going to be this first sample from this initial probabilistic grammar. Every new frame is just going to be training iterations for a Metasim method. So you can see the first frame was this car is being kind of randomly positioned, but then very, very quickly in training, Metasim already figures out and places these objects better. This is another example. And we're kind of iterating between which object type we're going to be optimizing for. I think we're starting with cars first, and then buildings and people. And of course, now you learn a generative model. You can actually sample from this model, and you can synthesize, infinite number of scenes potentially. And all is kind of tailored to your particular data set. So the question is, how can you evaluate the scene generator? And one way to evaluate this is by actually training a computer vision model, in this case, an object detector, on this data, and just testing it out of the box on the real target data set. And here we're comparing basically two ways of how the synthetic data set was generated, either using this initial probabilistic grammar, which is the first row, or our Metasim approach, which is the second row. So you can see there's some non-trivial boost in performance. All right, so right now we were discussing, the distribution for the structure was kind of well designed by the artists, and we were learning the distribution for the attributes. But maybe you want to learn the structure as well. So the number of lanes, number of cars. How can we actually optimize that as well? And we have this new approach, Metasim 2, that was just recently presented at ECCV, where essentially we're going to have a probabilistic context-free grammar, and which, if you sample from this grammar, you're getting strings. And essentially what we want to learn is a generative model of strings, such that when you render those strings, which are essentially these scene graphs, you're going to get good-looking images, so images that look like your target real data. All right, so under some grammar that the artist is going to define. So you essentially have symbols, which can be terminal or non-terminal, and every non-terminal symbol has a bunch of rules that basically expands it into new symbols. And how this works, you start with some start symbol, and you keep sampling rules until only the terminal nodes are left. Okay, so our generative model is going to look something like that. So we're going to sample this latent vector. We're going to map it to unnormalized, so basically logits over the rules. And we're going to use a mask for the rules that's going to tell us which are the valid rules at current time step, given the symbol that is the parent here. And given these valid rules, we're going to sample a rule, And we're going to do this autoregressively. So we're going to have an RNN that's going to now take this rule and again predict this unnormalized so logits of the rules, again apply a mask and sample again, right? And in the end, you're getting basically this string out, which represents a scene graph. Now, one thing to notice here is that this RNN essentially breaks this context-free grammar assumption because it actually kind of remembers what it has sampled before, which is actually quite powerful in this case. All right, so basically a sample of these rules is going to give you, a way to convert this into a graph. Then you only need to sample parameters, which is our previous work, and then you can render this scene. So I'm not going to go into this too many details, but essentially this problem is now a lot more complicated than the previous one, because previously we just had a continuous optimization problem, but here we basically have non-differentiable sampling in each step, right? We're sampling discrete number of rules here. So we need some sort of an RL to actually train this successfully. And we tried a couple of different things, including MMD as a way to compute the score, which wasn't working because MMD essentially gives you one score for an entire batch of data. So the credit assignment is just not working, right? You can assign credit to each individual scene. So Amlan and Jivan came up with this new parameterization of likelihood of each scene graph, and that's going to produce us a score for RL. And obviously there's a lot of bells and whistles here, and I'm not going to go into a lot of details. You can ask me later if you want. Results, again, on the right side, you have samples from Kitty. On the left, you have samples from probabilistic grammar, where now the structure also comes from some prior, both structure and the attributes. And in this case, the prior was really bad in a sense that there's no buildings, or maybe very few buildings, very, very few cars, no pedestrians. So it looks really far from the target Kitty images. And in the middle is this new, is this optimized scenes optimized from Metasim 2 plus Metasim, right? So we have Metasim in the inner loop here to train the parameters. So you can see that even though we didn't use any single label here, so no boxes or nothing, the model really learns how to place the number of objects correctly. So it starts to placing more pedestrians, more buildings, trees to match more to the target domain, as well as gets the parameters right, which I thought was quite nice. I really love this plot just to show how powerful this actually is, which was really surprising to me. And this is looking at the histogram of the number of cars for different, let's call them data sets that you get from sampling the grammars or from the target Kitty data set. So in dark green is basically the histogram of the number of cars for Kitty. So you can see there's the mode is around like, maybe 2 to 3 cars. The prior is going to be in orange. So you can see that it's heavily biased towards very few cars. And the learn is in the bright green. So you can see that the learn model is really getting close to the target histogram of cars, despite not using any labels, which I think is quite nice. And this is just evaluating the same model in this data evaluation regime. So training an object detector and testing it on the real case for different setups. Again, on the right side, we're just comparing the histograms, and here we're comparing the performance of this object detector over, just probabilistic grammar, if you only learn the parameters, and if you also learn structure and parameters. And you can see that you can get improvements in all cases here. Cool. So the next thing I wanted to discuss is objects, right? So this kind of learns how to place objects if you have some target scenes. And I think there's still a lot more to do for just making these grammars a lot more complicated with having a lot more objects inside. But another kind of parallel stream of work should be towards creating really good 3D models for individual objects, so that artists don't need to spend time on actually doing that. So there's been, so much work now that go from image or a couple of images into some good looking 3D model. And I'm going to talk a little bit about some of our work in this domain. And here is really where kind of AI computer vision turns to graphics to make like a really powerful training regime, where essentially we want to avoid having 3D ground truth, because a lot of the times we actually don't have for the real data, right? Unless you have some expensive sensor. And in graphics, we know that images are formed by geometry that interacts with light, right? So you have some mesh, you have lighting, you have texture, maybe materials, and then you have a graphics renderer that's producing a rendered image. And there's been a lot of work recently, not just by our group, there's many groups working on this, by making this graphics renderers differentiable. Why? Because then suddenly this full process becomes amenable to deep learning. How? Well, you have some input image or maybe a set of images that goes through some neural net that's going to predict these graphics parameters. And now through a renderer, you can produce a rendered image, and your loss can be entirely on the rendered image and the input image, plus maybe some additional losses that really make this thing to work, like multi-view consistency if you have multiple images, maybe some loss on the masks, and so on. Right, and if this render is differential, again, you can backprop the gradients directly to your neural net and effectively train this without having any 3D information in between. And I'm not going to go into a lot of details what we've done here. So we have like this rasterization-based neural renderer, but there's quite a bit of work recently on having all sorts of renderer in the loop. So our results were here, and this was some results on ShapeNet, which kind of looked good and exciting at the time. And this was on some real data. Now, if you look all these differential rendering papers closely, what really kind of makes them to work is all these additional losses. In particular, for this input image, people have key points, they have masks, and so on. And then you can get pretty good looking birds out. And then we apply this exact same model on the Pascal data set, which is maybe smaller and has a lot more variation of objects. And it turns out that the results were really not good. Right? So in this case, on the right side is the baseline, which is, I think, some work from Berkeley a couple of years back. And in the middle is ours. And both of them look pretty bad, right? And so what I'm showing here is just reprojection of the prediction into the image plane. And then we kind of attribute the problem to data, just because the birds were working pretty well. Again, the reason being that Pascal has maybe fewer cars, and maybe those annotations are somehow not at the same level, or maybe there's just so much more variation in these cars for this data set, right? So this was kind of bad, and fine, we set problem with data, and the question is, what can we do now to make this better, right? So how can we get data to remedy this? And of course, one way is you go out and take pictures, maybe at a car show or something, to take multiple views on cars, and then you have NeRF and all that you can produce some maybe good 3D reconstruction. But we kind of turn to StyleGAN, because StyleGAN already is a really good synthesizer of images, right? It produces really good looking cars that looks like real cars. And if you start kind of poking into StyleGAN, you find a lot of really interesting things. In particular, you can find part of the latent code, which is responsible just for viewpoint, and the remaining part is responsible for, let's say, content, where content means the type of car with maybe some scene variation as well. So in this particular case, we're going to keep the content part of the code frozen, and we're going to just be changing the latent code for the viewpoint. And you can see that it's basically StyleGAN is rendering, a neural rendering, this kind of same car in different viewpoints. You can see that it's not perfect, but it's pretty believable. Maybe enough believable to actually plug it into our differentiable rendering pipeline. Okay, so basically there is also a different effect. So if you keep the viewpoint code fixed, so in this case, different columns are going to be different latent code, so different viewpoint, but vary the content code, you essentially, there's huge consistency. Basically, StyleGAN is rendering different cars in that particular viewpoint, quite consistently in terms of pose, which is great because now you have this neural synthesizer of the data that you basically want. You can have control over the viewpoints and you can synthesize any number of cars in that viewpoint. And that's basically the data we need. And we didn't basically change anything in our framework with the differentiable rendering training, except for the fact that we allowed the viewpoints, so we treat it as a latent variable. So we jointly optimize it with the model, just because the viewpoint is a little bit noisy. But apart from that, the differentiable render was kept exactly the same. And the only thing we changed here is the data, where basically how we're using this data is to impose multi-view consistency during training across these different viewpoints. All right, so these are the results. So on the left is some input images. The second row is the render prediction in this kind of input view. And then you can see this prediction and render in different views just to kind of appreciate the different shapes maybe and textures that the model predicts.
Hey, Sanja, can I ask a question?
Yeah, go ahead.
How did you actually find this viewpoint code? Like, was it a trivial, like, one element in your latent code, or how did you find that?
I think it was just like the first 4 layers in StyleGAN. It was very simple search. We spent an intern doing this for a week.
Okay.
I think the StyleGAN paper already hints at this a little bit, and we kind of follow their lead. And we found that the same kind of regime also works for StyleGAN too. And again, I think in the future you can maybe automate this. Maybe we can find this automatically, but here we just manually, we were just kind of figuring out which layers could be responsible for viewpoint. And it turns out, I think it was this first 4 layers.
Okay.
The paper should be out in like 2 weeks, so the details are going to be there.
Okay, thanks a lot.
Yeah, and this is just comparing this exact same method, but just changing the data. So in the first row, you have this kind of StyleGAN data set, and the second and fourth row is the Pascal data set. So you can see that it's basically like a pretty drastic quality difference between the two. And of course, now you have this method that can go from a single image to pretty good looking cars, right? And obviously, I think in the future for a real product or whatever, maybe we want to have multiple images. But if you can do what you see here from just a single image, I think this is pretty amazing. So this was just my little test. So I don't have a car actually. I just did my driving license like a week ago. I drove in Slovenia, but not in Toronto. So I need an Ontario driving license so that I can finally put like a dream car here in my parking lot. And of course, what can we put there? Can we render something really good? And we were trying basically our model on this very fancy cars that, are never part of StyleGAN data set. And it turns out that it doesn't really do so well. I mean, it kind of tries to produce something reasonable. You can see that little bump in the front, but it's nothing like a Batmobile in this case. And we tried a full bunch of these kind of odd cars. So essentially what this model is learning internally is some priors on how these cars look like. So if the input is a car that it has seen in or close to the cars it has seen in the training set, it's going to produce a really good result. If it's something completely out of distribution, it's just not going to do a great job here. So for example, for Mr. Bean car, he's doing a pretty reasonable job, but for Flintstones and whatever is really not good. So basically, we have this here for now, but we're working on improving this. I want a Batmobile in the future. All right, so here is a little demo where we took this Omniverse tool that you've seen in the beginning in the initial video as a 3D visualizer. We just loaded up some scene from TurboSquid here. And we're taking, now the user can take a picture and just place it here in the scene. And one thing to notice here, which I like really a lot, is look at the materials of these cars, because we are now actually also able to predict a little bit more As you can see, we can predict the part segmentation, a really detailed part segmentation for these cars. And we can use this part segmentation to place correct materials. So you can make the lights emissive, you can make the windshield transparent, and so on. So I think this is pretty cool. And now you can actually do, Metasim, which places objects with these fake objects from pictures. As a very, very simple first demo. And it kind of works, like the tires are not great. So if you take this autonomous driving camera view, you can see there's quite some issues still. But at least for the objects that are far away from the camera, it looks pretty believable, right? So maybe you can already start using it for at least cars in the distance or something. And and I think in the future we can make this better and better. Okay, cool. So we did one step on top of this for this StyleGAN idea, where now you can think of using StyleGAN as a multi-view data generator, so that you can train this, let's call it inverse graphics network, to predict mesh, light, and texture. But you can also close the loop, right? Because now essentially you can go from latent code into mesh, light, and texture. But we can map that back, this graphics properties back into a latent code, and send that through StyleGAN to synthesize an image. So potentially we can have this kind of neural renderer, right? Where we can take, standard CAD models and use StyleGAN to render them. And there are just small details here, right? So we have basically camera, mesh, texture. This goes through some neural network. And the only thing that we kind of impose on this mapping between graphics into the latent code is that it's trying to disentangle the latent code. So for example, we're trying to make each dimension of the latent code be explained only with one of the input graphics parameters, either mesh, texture, or background or camera. And we train end-to-end this entire pipeline. So we fine-tune StyleGAN using all sorts of different consistency losses. All right, so here we have some input images, and we make a prediction out of these images to get mesh, texture, and whatever. And now we can use a graphics renderer, like this OpenGL renderer, to render those graphics properties into images. So this is the second row. But now we can actually map those graphics parameters back to a latent code. So we can have this neural render, and we can render back with StyleGAN. So this is kind of like a neural rendering with StyleGAN. So you have this kind of dual renderer where graphics and just this image synthesis approaches are kind of competing. And the nice part about StyleGAN as a renderer is that it actually captures light, like the secondary light effects and background, much more effectively, at least, than what we can do right now with our simple OpenGL render in our setup, which I think is pretty cool. All right, then one thing that I also wanted to touch upon, just kind of linking into dynamics, is kind of rethinking representations that we're using in 3D reconstruction. So right now, if you have some input image, point cloud, and you want to predict some 3D reconstruction, some 3D output, there's different ways to represent the output, right? So people have used voxels, people have used meshes, sign distance fields, and point clouds. And all of this, I think, comes with some pros and cons, right? So voxels typically need some way of discretizing the 3D space. And it basically allows you to deal with arbitrary topology, but lacks geometric detail, just because you need to have some discretization, right? Or memory just blows up if you want to have really high resolution. Mesh as an output typically assumes you have some sort of a template topology, right? And right now, at least in our case and some other works, they assume some sort of sphere topology, right? So maybe you have geometric details, but the topology, or at least genus of the prediction, is fixed, right? So you get these funny artifacts in this particular chair example if you're using a sphere topology. In SDF, you can handle infinite resolution, right? We've seen all these nice works these days. You can have arbitrary topology, but it requires this post-processing and some regularization to work, right? So typically people use marching cubes, and this is also not super fast. It can take a few seconds to decode. Again, point cloud is a little bit like, it's somewhere in between, I guess, the two, so it can be pretty lightweight. It can have an infinite resolution, but again, it's a little bit hard because you need some post-processing to get the mesh out. Okay, and what I want, at least, and I think maybe what we want as a community, is it has some representation that can go from input into, you know, something that can enable simulation, right? Or, you know, planning, gaming, or whatever. We want to predict something that can directly go into simulation and be differentiable, because then you can exploit, you know, physics-based simulation and so on, maybe in an end-to-end way. So what we have been looking at into is this other graphics representation. Somehow people have not yet used in the 3D reconstruction community, and this is tetrahedral meshes, right? So this representation is basically exclusively used in physics simulation, right? All these finite element methods essentially operate on tetrahedral meshes, right? Where basically this basic element of this volumetric mesh is a tetrahedron. Okay. So this our approach that we're gonna talk about here is we're gonna do something like voxels, but we're gonna be closer to something like this SDF or this infinite resolution network, and we're gonna do something in between. In particular, we're gonna first assume that, you know, every object lies in some unit cube or whatever. We're gonna have some uniform partitioning into this cube into tetrahedrons, and that for each tetrahedron now we're gonna try to predict the occupancy, which is the same as what people are doing in voxel-based representations. But we're also going to predict the deformation of each vertex. So essentially, we're gonna try to locally adapt the geometry to better capture details, but still remain in this kind of low-dimensional regime, right? Where we want maybe have a 30 by 30 by 30 tetrahedral mesh, but because we can deform the vertices, maybe that's enough to represent really high-resolution geometric details. So essentially, our network is going to do something like this. So it can take anything as input, like point cloud or image, or, you know, anything. It encodes this, and then it starts basically from this uniformly spaced vertices of a tetrahedral mesh, and decodes two things. It decodes tetrahedral occupancy, and it decodes the formation for each tetrahedron. And basically, we have a bunch of different losses here to train this. So our construction loss is trying to train both occupancy and deformation, such that, you know, you're close to 3D ground truth object or surface. At the same time, we can also do, you know, differentiable rendering in the same way. And a couple of regularization losses that essentially says, you know, that the surface needs to be smooth and so on. I'm not going to go into details. The paper should be out in about 2 to 3 weeks, maybe end of September. But the inference is super easy here, right? So the network output is occupancy and deformation. You're basically just thresholding the occupancy, and that's it, right? Then you get your object, and everything is differentiable. So you can think of really great potential for simulation later on. So a couple of results. So here we're just gonna do point cloud 3D reconstruction. So the input is point cloud, and we wanna predict a 3D shape. In our case, it's going to be this tetrahedral mesh. So you can see different methods, and on ours is on the right. In terms of performance for this particular task, if we just look at speed, so we are about 85 milliseconds here for one object, which is maybe comparable to pixel to mesh, but we are a lot better than them. And kind of at the same level of accuracy, which would be ArcNet and mesh RCN in this case, we are significantly faster. This is like an order of magnitude faster, because we basically don't need any post-processing like deep marching cubes. This is comparing just the aspects of deforming these vertices in this method, as opposed to not deforming them. So be close to this kind of voxel representation versus this deformable representation. I think in orange is IOU, and in green is chamfer. And I think the dashed lines is voxel-based representation, and solid is our def-det approach. So you can see that there's a huge boost in performance given the same resolution. So you can do a lot better. And if you just kind of look at this, so basically at resolution 30 cube, you can get pretty much the same performance as 60 cube for voxels, right? So this brings you almost like an order of magnitude in efficiency, at least for memory and also probably for computation. This is single image 3D reconstruction using 3D supervision, right? So this is really a representation that can be plugged into all these different tasks, essentially. So this is just ablating single image 3D reconstruction if you have 3D supervision. And the nice thing here is that this is basically the first result. You can just go from an image to TET mesh, which is not trivial. And this is using differentiable rendering in the loop. So you can do single image 3D reconstruction with just 2D supervision. And we can get basically comparable performance to some existing approaches. But again, we get directly TET mesh. So now we can do all sorts of cool stuff in the future with this. This is just a result, I think, that we got 2 days ago. So I won't to put too much emphasis on it. But we're just comparing this for multi-view 3D reconstruction. On the right side is going to be NERF. On the left is our approach with predicted depth in the middle. So, it has this small artifact just because we still do have a limited resolution to some extent. But it's significantly faster. I won't quote numbers right now because I think we can do a lot more optimizations on top. But it's looking at least an order of magnitude faster. Cool. A lot of the stuff that we've done is available in this 3D deep learning library called Kaolin. We released it a while back. And a complete reformat is coming in October. So it's going to be a lot more optimized, a lot more non-researchy, so more professionally written. And it's going to come with a lot more goodies. One goodie is going to be a visualizer. So you're going to have the Omniverse, or this visualizer I was showing before, as a way to visualize your results. But one cool feature is also going to be kind of like a tensor board, where you will be able to see how your models are training. In this case, this is for our differentiable rendering work I was showing before, where you can kind of see through iterations of training how your models are improving for either aspects like texture, shape, or parts. Cool. I don't know whether I have a little bit of time. I maybe need like 3 more minutes. Is that okay, or should I stop?
Go ahead.
Okay, cool. Yeah, so the last thing I wanted to talk about is going a little bit toward dynamics and modeling time. And I don't really have a lot of results on this, but I just wanted to mention so that maybe people get inspired to work on it. And there's some really cool stuff coming in October. It's going to be timed with a new release of Kaolin, which is going to be a differentiable physics simulation. Nvidia has really good physics simulation. And we're going to release in differentiable physics, basically library, which is going to be in parallel to Kaolin, as well as a link between the two libraries. It's basically, you're going to allow you to learn, both geometry and physics parameters from videos. So this should be coming in October. And really, just for kind of modeling dynamics, I wanted to mention this work, GameGAN, which started as a fun project, but it's becoming so much fun, we just can't stop working on it. And the idea is, in computer games, you have user action, and then the game engine is basically computing the next state, and then it renders output image. And we were asking the question, can we learn like a differentiable simulator, essentially, right? Can we try to replace the game engine? Can we just look at gameplay and then learn how to simulate the game, right? Learn the environment dynamics, and then be able to take a user action and produce the screen using a neural net. And we released this this work basically on the 40th anniversary of Pac-Man. So we trained this model, which is essentially like an RNN, basically with smartly designed losses to replicate Pac-Man. So basically now a user can play with GameGAN to play Pac-Man. I'm just going to play this video. What you're seeing is rendered by GameGAN, and it's quite amazing in my view that you can learn, that if you touch the food disappears, the ghost can be blue or not, and if you touch a blue ghost, it disappears. It looks like the level can kind of learn this very simple rules in the game. Cool. So we've been developing things further, maybe going towards more serious or more complicated 3D games, and eventually maybe to simulation from the real world, where you can take like a drive from a real self-driving car, and maybe we can learn how to simulate the world basically by looking at that play. So kind of going towards that vision. We have some very initial results here. So. And then the left one is trained on Carla, and the right is trained on this Gibson environment, which is like a real world navigation environment. And on the left of each, you're going to see a control. So this is Seng, who is the lead author on this. He's playing a game with his GameGAN++. And on the right side is going to be the rendered screen with the network. So the original GameGAN doesn't work so well on this because it's a lot more complicated, right? You have an object and you have the entire scene. So a lot more objects in the scene, and it's all 3D. But this new model is doing quite a good job if you look at it. There's some really funny effect, like if you try to drive the car onto the sidewalk, the GameGAN essentially learns to change, like prefers to change the environment rather than you crashing, just because I think it hasn't seen a lot of crashes. Yeah, so this one was trained without any other objects. And we have like really, really recent results. So don't take this at face value, it's gonna become better. If you actually have other agents in the loop as well. So if you train Carla where you actually have other agents in the environment. So I'm kind of surprised, like there's quite good temporal consistency, and the objects are kind of there. So it kind of internally learns some behavior, but they change in appearance from time to time, like that car became red to blue. But it's kind of learning something good here. And on the right side is essentially this navigation environment in Gibson. So you can now kind of navigate in this fake world. And again, there's quite a lot of 3D consistency here. Yeah, so, this is what we have so far. I think this is just really the beginning. And, my talk is more to inspire you to also work on this domain. And I know you already do. So maybe I don't need to convince you. But basically, ultimately, we want to create some tools that are going to democratize 3D content creation, right? So anyone, even like my mom or something, or my niece, should be able to create really good looking 3D models. And then maybe AI tools for more professional users like artists to create like really high end content. And then, maybe put all this together to create much more scalable simulators for robotics, such that all this doesn't need to be purely designed by hand. And, like I said, this is just the beginning. So I think there's a lot more stuff that we can do here. Yeah, thanks for listening.
Oh yeah, thanks so much. I mean, this was really fantastic. We have a lot of people. We have already a lot of questions on YouTube, so I have to monitor it a little bit. So if anybody has some questions on Zoom, just speak up and ask. And maybe I can start with a bit of a high-level question. So, I mean, what I think is pretty interesting, right? Of course, a lot of the work you're doing is motivated by you want to get basically 3D content. You want to make it easier to create all the massive contents you need for like games and movies, right? At the same time, though, right, there's kind of a trend, like specifically when you go to GameGAN, like maybe we don't even need the explicit 3D content, and we rather encode it in a neural network. So where do you think this trend is going?
Yeah, and this is why we're also attacking this problem from both ends, right? Because it's much harder, I feel, if you really want to go into this graphics domain where everything needs to be this perfect 3D content, versus everything can just be done on image level with some neural renderers, right? I don't know. I think both are gonna improve, right? I still like this explicit modeling of geometry and texture, just because graphics is really advanced, right? And they have all this, rendering, which can take into account lighting and occlusions and physics simulation. That might be hard, at least for now, just with these neural renderers. But I might be wrong. I think it's worth exploring both directions. So I'm not sure.
Yeah, I think it's tough to say which is going to win, but I assume it's going to be somewhere in the middle. I think you definitely want to have some sort of 3D representation.
You want to have some learnable 3D representation in the middle, whether it's explicit 3D or it's just some sort of a image-based latent code. I'm not entirely sure. Yeah, I mean, the same as 5 years ago, we thought GANs are just not going to produce anything meaningful. The images look really crappy, right? But these days, these faces are like stunning, right? So who knows?
Any other questions on Zoom? If not, I'm going to ask a few interesting questions. So there were a specific question was about Kaolin. So they wanted to have a few pros and cons compared to PyTorch 3D. Can you say some about this one? Like what do you think is the? I mean, I think the physics sounds really amazing. That one I have not heard of, but I guess that's going to come out in October, right?
Yeah. I feel like what we released for Kaolin was maybe more researchy code, and PyTorch really did a good job in having software engineers develop something maybe a little bit more polished. But we've been working on improving all that, right? So the new reformat is going to be, it's going to have all these ops and everything is going to be optimized. So I feel like we're going to reach that level of polishing soon, but it's going to have maybe more links to other things, right? So one thing is visualization, another thing is this physics. I think it's going to be a huge advantage.
I'm super excited about the physics. I think that one is going to be really cool, right? It's not just static reconstruction, but then you can take full videos and getting the whole dynamics. That seems pretty new.
That's right. Yeah, the research physics group has been working on their differentiable physics, and we kind of wrote like a link between the two, so everything can hopefully be used together. So that hopefully comes out end of October. That's the target, but it's always with a bit of delay. And I think visualization is going to be really cool because this has been so much effort in this omniverse, and I think all our results are going to start looking at SIGGRAPH level with that kind of visualization. The initial Kaolin had some advantage, I thought, with having a lot more examples, right, where people maybe could just use existing code, which were tailored to have Kaolin at the base and quickly compare them. But yeah, I can't say much beyond in favor rather than that. But I think the new version is gonna surprise you, so stay tuned.
We will definitely try it out. Any other questions? Come on, somebody on Zoom. I mean, I have a lot of questions on YouTube, but I mean, maybe somebody else wants to ask too.
I actually have a question regarding like the explicit representation. Like for faces and GANs, like we have seen like this, great works and like really stunning results. But on the same end, in 3D, there is still like a lack in terms of quality, I guess. Like, do you think what's your opinion? What's missing there? Is it like just the availability of data?
That seems to me like the major roadblock, right? For GANs, people train on these Flickr data sets, which are huge, right? And you need quite a lot of data to train really good GAN models. At least that's been my experience so far. And in 3D, you have ShapeNet. There's not much more beyond this, all right? Which is very limited by nature. I don't know exact numbers for how many cars you have. Plus, there's variations, right? You can have viewpoint and color. I don't know what makes it more hard. So also these representations are probably less mature than image representations. I think maybe 3D community is also a little bit of catch up, right? So I think my guess would primarily be data, and the second would be I don't think we have fully converged on the right representation yet. And maybe there's opportunities there, right? Like voxel-based representation basically depend on the viewpoint of the object, on the orientation of the object, which probably is not great. Or this implicit function is basically x, y, z to some distance. It's basically memorizing things, right? And then maybe latent code can help, but I'm not sure whether we have like fully converged on a really good representation that can be, rotational, viewpoint invariant or equivariant or something.
There's actually a couple of cool work, like in the ML community, they have these spherical convolutions and stuff like this. So in principle, they are equivariant.
Yeah, that's true. Yeah, spherical convolutions, you mean? Yeah, but at the same time, they need to map everything to a sphere, so they cannot just take arbitrary topology.
Yeah. It has pros and cons. I mean, it's pretty interesting. Like we had a bunch of, like we did this Matterport 3D data set, right? And these ones are actually Panophews. So for these ones, you can actually map it to a sphere. But for general environments, maybe not.
General objects, but I mean, Matterport is really good already, right? But it probably is also noisy because it's point cloud, so maybe you don't have like perfect 3D. Like, do you think you can train a GAN on that kind of data?
I think so, actually. I think it should work. I mean, the full scenes might be still a bit tricky, but at least for like local objects. 3D, well, for objects for sure. But I would expect you can get this for rooms as well, right? We had a couple of works. We had this like Max Jiang and with Tom Funkhauser and these guys. We did this one work where you basically take point clouds as input, and then you can already get a pretty good reconstructions on the scene level.
Yeah, but like again, that would just be generating chairs, for example.
I understand.
Have you guys tried that? Yeah.
Well, not quite, right? But I'm saying like the next step is like if you go into like purely generative tasks there,
you could do that,
You probably can get there, right? You do it in some sort of patch-based multi-res version, and like I mean, again, but I think for small objects, I think that's already been done. I've seen a few things that works, but I think the interesting thing is if you could get the whole scene, the whole floor, like an infinitely large. Like think about in the game, right? Like similar what you do in game GAN, when you could under the hood generate like a 3D representation. You move around and on the fly it would kind of
but it's hard. It's super hard to get objects there. Like if you see, it's still kind of blobby and not consistent. It's super hard to do it at the full scene level. And we were trying on something like Coco style data, and that even has so much more variety. That's super hard. I didn't find good GANs for just synthesizing full scenes.
Yeah, I mean, Manu is, who just asked the questions, he's actually working on that kind of project right now.
Great.
At least getting it for a frustum to work.
Okay, awesome.
Even that is hard.
And do you think that it's a problem of data or a problem of representation?
I don't know, Manu, what do you think?
I mean, the step between going from shapes to scenes or like scene crops or rooms, whatever, is like huge, right? Like in at least those few shape GAN papers, there you had like canonical shapes and I think single class GANs, like usually you train one GAN for each class and then ramping this up to like full scenes or rooms, like here you have like huge priority.
Yeah, I don't know, chairs, I think it's hard. We were trying to train just image-based GANs for chairs, and that was hard because there's so much variation in chairs and there's these thin structures that are not like super well aligned. Maybe it's easier in 3D.
Did you try it on what did you try it on data?
I think we just took like open images or something like that, the chairs. Maybe it's too much occlusion or something, but it didn't produce anything like too exciting.
Well, I mean, maybe you go the way, right? You first generate a 3D voxel grid that is rough, and then you synthesize some neural pixels on top of it.
Yeah, that's right. Maybe that's a good way. Yeah, like a 3D representation might actually be more kind of aligned.
I mean, the challenge is, right, like if you go in a full GAN setting, you have to have you have to basically learn the distribution of it's very tricky, right? Because the longer you make this chain of intermediate predictions, like the distributions get much harder to learn.
Yeah, that's true.
But I think it's a cool direction. I mean, I don't know. I feel like what you've done in the Metasim work, maybe this kind of stuff could work there too. That you have a fixed set of pieces and you just restructure them. They're close enough, and then you have like a GAN that makes it look like this one image or something, right?
That's right. Like we were thinking that if you can just have a GAN for each of the objects, and then the synthesis just kind of like saying where you want to place them.
Yeah.
The Slayton vectors, right? So
that seems cool, right? I don't know.
Yeah.
I mean, we're still trying to learn everything and encode it in a series of consts, right? Like it's like we have very little insight in actually like what. In fairness, StyleGAN does a good job in terms of disentanglement. that is surprising in a sense, but in principle, in the long run, right? Like about the 3D structures, like the GANs, we have no clue what's going on really.
Yeah. True. I
Okay,
think for faces,
unfortunately,
people had some success for 3D GANs, but
yeah,
not general objects.
I mean, we're running a little bit out of time. I think I'm a bit sorry for all the people on YouTube. There were actually a bunch of questions. Unfortunately, the good thing for us is we will still have your hope. You're still going to be around for a few minutes, right?
Yeah, I can stay around. Yeah,
okay.
For sure.
So I'm gonna end the stream now. It was really great. I think everybody enjoyed the talk. I'm a little bit sorry for all the people who asked the questions, but maybe they can just send you an email. And
yeah, why don't they send me an email? Yeah, sounds
okay,
good.
cool. Yeah, thanks a lot. I'm gonna quickly end the stream here. Okay, so here we ended.